Morning. So I think we have a nice introduction with the previous speaker about extracting behavioral models of transistors. So in fact, we will follow this discussion with an exercise we have done following more or less the same approach, but in fact, we have used such a model in order to design an amplifier. Because in fact, when we are using behavioral models, we can see some issues specifically about convergence when we are simulating the amplifiers in interpolated or extrapolated areas regarding the load impedance. So in fact, when we want to design an amplifier, there's different solutions today. We can use different kind of models, physics models, compact models, or behavioral models. Each family of models have its own drawback and advantage. The main drawback of behavioral models are the limitation, in fact, because it's a table-based model. There's no physics aspect into these models. So if you want to extend the operating range for these models, it's a bit tough because, in fact, you need to take care about what are the measurement conditions which have been used to extract such a model. So the intent of this work was to try to enlarge a bit the area to use such a model. When you want to extract a model for a transistor, in fact, if it's on wafer device, that's fine because you can use some basic approach such as pulse IV, pulse S parameters to extract the models and load pool measurements to refine the model according to the frequency of interest. When you are dealing with packaged devices, it's not the same story, in fact, because in addition with the transistor model, you need also to extract some additional elements, such as, for example, the model of the package. And you, inside the package, you also have some bond wires, and you need to extract a model for all these bond wires, plus you need to take into account the coupling effect between these different wires and so on. And finally, you have to try to make a global model for the package, for the wires, for the die, and you have to refine your model against S parameter measurements, against load pool measurements, so you can really spend a very long time on this task. Basically, if you start from scratch, if you don't have an existing model on your device, you can spend up to 3 months to develop such a model. So if it's a foundry, that's fine. You can put some resource on this work and try to spend time knowing the fact that you will reuse all this knowledge for the next device you want, for which you want a model. But if you are a designer, you won't spend 3 months of development to, just to make a PA. So you need to use other solutions. This is why behavioral models make sense, in fact, because from the perspectives of the power amplifier designers, you just need a tool. You don't know about, you don't care about how the current source behaves and so on. You just know what are the biasing conditions you want to use according to the transistor you will choose. And from this, you will define the operating conditions, that is to say the frequency of interest regarding load pool measurements and so on. And you want to use all this knowledge to extract a mathematical model, black box model. So we tried to do this using the same component that we talked earlier, that is to say 10-watt GaN devices. And the aim was to make an exercise in order to design a Doherty amplifiers. So in such amplifiers, in fact, we have some dynamic load modulation according to the instantaneous envelope of the modulated signals. So because of these dynamic load modulations, if we want to run an accurate simulation, we need to make sure that we have the tools which are ready to use in order to take into account these dynamic modulations. So the model has to be accurate over a wide range of power conditions. It has to be accurate over different loading conditions. And obviously here we have a class AB and class C amplifier, so we need to have a model for each class. So first question could be, can we just use load pool measurement to make such a design, in fact? it's not easy to just use load pool measurement because of the dynamic load modulation. We are not in a static condition regarding the loading conditions for the class AB amplifier, for example. So it's tough to just use these measurements unless we are using some interpolated processing tools and so on. But it's not straightforward. So here it's just to illustrate what we would like to achieve. That is to say, we want to extend the maximum efficiency range for a given output power according to this dynamic load modulation. So we have developed a solution which is using some Mori product. So we have the solutions that drive the PNAX and the comb generator plus passive tuners, and we can also address some active load pool using external active sources. So in fact, here the idea is to drive some load pool measurement not around 50 ohm, but in the area of interest regarding the loading conditions. That is to say, the load impedance which will be seen by the transistor when this one will be used in the Doherty design. So we started with a classic approach, which is a polyharmonic distortion model, in fact, where we will probe the influence of a small probe tone here, which is applied for a given nonlinear operating state. And if we shift the phase of this probe tone, in fact, we will measure the response of the small perturbation over the full spectra for the output B wave on the input and output ports. So here, nothing new. It's just the starting point. But if we are using this static model, in fact, it's not enough to address a design such as a Doherty amplifier because it's a basic EPHD model. It's just a linear description around a nonlinear state. And if we are using this formalism, basically we will have a table-based model where we just, as an illustration here, we in the purple point are the impedance which has been used to extract the model, and the blue circles are the area of validity of the model around this extraction. So we can see that if we have a dense grid of measurements, then okay, it will cover the area of interest. But in the Doherty amplifier, we can have very strong load modulations, and we can go, for example, in interpolated or extrapolated conditions. And if so, we may encounter some difficulties. So if we are just within the blue circles, that's fine. We have a good fit. So here it's just an illustration of the class AB and class C load conditions which are seen by the transistor when we applied different power levels. And we can see that we can go even very close to the Smith chart area. So can we use such a model? Maybe no. So this is why we have developed a new formalism in order to cover a wider area, in order to better address this interpolation and extrapolation needs, in fact. So we have extended the description, the formalism. So rather than just using the first order probe tone in order to probe this nonlinear behavior, we are using a third order expansion, in fact, to add terms in the model in order to better define the nonlinear behavior around a nonlinear state, especially regarding the loading conditions. So how does it work in real life, for example? So we have used the 10-watt GaN amplifiers. So we made some basic load pool measurement, harmonic load pool measurements. So we found that the optimal impedance at the fundamental frequency was here. So what we have done for a fixed harmonic load impedance in the area of interest, we swept the fundamental load impedance to cover an area where we want to focus. And then, in the second step, we fixed the fundamental load impedance, and we swept the first harmonic load impedance. And finally, we fixed the fundamental and 2FO load impedance, and we have swept the third load pool impedance in order to probe the behavior of the transistor response when we swap this harmonic impedance. So a good point for this methodology is that we don't need to use tickle tone anymore. There's no small prop tone perturbation with a phase shift around a nonlinear state that consume a lot of time during the measurements. In fact, we just run calibrated harmonic load pool measurement, magnitude and phase calibrated using a comp generators. And because there's no tickle tone applied for each nonlinear state, for each load impedance, we can really reduce the time needed for measurements, because even if classic EPHD model has some limitation regarding the interpolated conditions, we have seen that in the industry, the main barrier for the adoption of this formalism was the time spent in measurements. People don't want to spend one day to measure one transistor for one bias point. It's just too long and too heavy to manage. So the time spent in measurement was really important. So now we will see how to use such a model into a real design. So we used again these famous 10-watt transistors, and we have extracted a model in class IB condition, in class C conditions, and we try to design a PA using this model. So, and we also made a benchmark using the legacy EPHD model and this enhanced EPHD model. So in order to have a fair benchmark between these two models, in fact, we use the same density of impedance grid to extract this model. So our model has been done with the purple cross here, and the classic EPHD extraction has been done with the blue circles. So we have more or less the same density. And the harmonic impedance has been fixed to the optimal area during these extractions. And then we tried to evaluate the model behavior for some load conditions which has not been used for the model extraction, because often we see, okay, we have a good fit between the model and the simulation, but we show the model performances on the same impedance which has been used for the model extractions. And so we can't evaluate how the model is efficient in these conditions. So we try to use, for the model and simulation comparison, we use the red point, which are interpolated conditions. So if we look at the response of the classic EPHD model in these conditions, we can see a fair let's say a fair agreement between the measurement and the simulation. Maybe we have some small difference here about the input impedance, the magnitude of the input impedance of the transistor versus power level and versus load impedance. But more or less, that's not bad. Using the EPHD, we also have good results, and we have been able to fit a bit better this input impedance of the transistor. Maybe this parameter looks a bit exotic, in fact, for some of you, but in fact this one is very important, because if you are able to fit well the input impedance of the transistor versus the power level, then you have a very good chance to fit well the transistor power gain. And now we challenge a bit this model in harder conditions, that is to say in extrapolated areas, where we make some comparison between the model prediction and the measurements in some areas far from the location used for the model extraction. We have been able to see that if in some loading condition we have no convergence at all regarding the simulation. So definitely we had some issues for certain conditions because in fact you can see that the input impedance of the device is very, very low. It can even be negative for some load conditions. So it's hard to make a simulation in those conditions. Because of the higher order of model description with the EPHD, we can see that even in tough conditions where we have almost a negative input impedance, we still have a good behavior looking at the model prediction in these extrapolated conditions. So this was for the class AB model. We have done the same exercise for the class C model. So class C model is again a harder conditions to evaluate the model capability, in fact, because of the strong nonlinear behavior looking at the power gain curve. So we have no power at low conditions, and we have a sudden gain expansion at high power, and we need to be able to fit this hard gain curve shape. So with the classic model, we can see that when the input impedance is close to the Smith chart, the edge of the Smith chart, then we can have some discrepancy. And with the EPHD, again, we have been able to predict even the unstable area, that is to say when we have negative input impedance. Okay. Class C is the same for extrapolated conditions. So we push against the limit. So we can see that in extrapolated conditions, for some certain load impedance, it doesn't fit at all. While with the EPHD, it works. So, and the conclusion between the benchmark between these two models, we can see that for both interpolated and extrapolated conditions, this higher description, this higher order of nonlinear description can bring a significant advantage when we are challenging the model in very hard simulation conditions. So it was the first benefit, and the second benefit was really to reduce the measurement time spent during the measurements. So we have designed a Doherty amplifier using these two different models, and we made a simulation at the circuit level for using both class IB and class C models simultaneously, and we also made a measurement of the power amplifiers to see if we were able to predict the performances of such an amplifier. So here it's a benchmark, not at the transistor level, but at the circuit level. And we can see that both models are able to predict the overall performances, but if we just use a first-order nonlinear description, then we can have a significant error looking at the output power which is simulated, or even at the efficiency, because in some conditions the output current is not really well predicted because of these dynamic loading conditions mainly. Okay, so I split my presentation in two parts. So this was the first part about the concept and the approach we have used. I can show you how we extract the model and how we use it into AWR, for example. So here it's a 5 minutes video. It just shows how we manage this. So first we take the load pool measurements, and we can just make sure that we have good trends of the data into the visualization tool. So we will just look at the model, the data which are being used to extract the model here. So we have different AM/AM and AM/PM curve for different load conditions that will be used to extract the model. Once we have all of this data, we will try to extract the behavioral models. And in fact, we will, just before extracting the model, we can use some post-processing data in order to make sure that we have a good behavior for each kernels of the model. Because if you look at the kernels of the model, such as, for example, so here it's with, let's say, the S11 versus power and versus frequency, and we have some discontinuities also on strange phenomena that comes from the measurement world, then it will not be good for the simulation part. So before extracting the model, we observe the kernel response versus frequency and power. We can apply some smoothing functions, some filters versus power levels versus frequency. And once it has been done, we can extract the model. So here we will extract the model for an harmonic balance simulations. So each kernel is fit for versus power and versus frequency. And once it has been done, we can export this model into a file. And later on, this file then will be loaded by the simulator in order to run the simulation. Okay. So here we are saving this demo model, in fact. So the purpose of the simulation here, it's not, this one has not been done in this presentation at the circuit level, it's just at the transistor level. But the aim was to show how to manage a model when this one has been exported from the measurement solution. So first we will load some load pool file. In fact, so in Microwave Office you have some template ready to use to load the CST file, which are generated by IVCAN. So, and then we made a template where you will be able to load as well as EPHD model. So here it's a load pool simulation template. So you mostly, probably you better know this one than me. So we can define the loading conditions, the bias conditions, and so on, the harmonic conditions. So here we will try to find where is the model which has been exported from IVCAD. Okay, so we have a library when this one has been stored, basically. We'll drag and drop the model here into the simulation template, and we need to have to connect the transistor model to the outer world. Okay, so we will define basically what is the model we would like to use. So for example, for class AB or class C conditions. And then we still have to maybe define some parameters, additional parameters, looking at the frequency, the carrier frequency of interest, the power range that will be used, and so on. Okay. And now we are ready to launch a simulation using this model. So here it will be an harmonic balance simulation. So we will define so here we just did the exercise for some load impedance, again, which has not been used for the model extraction. So here we just look at the interpolated load conditions which has been shown previously on the slides, in fact, just to make sure that we have good match even in these interpolated conditions. So using the NI template, we can define the voltage, current to bias the transistors, and the loading conditions, so it's quite straightforward to use. We can simulate the response. Okay, so we made some update into this template. So we have some warning message. And now we will be able to visualize the main figure of merits for these loading conditions versus different power levels. So we can visualize, for example, the input impedance of the transistor versus different power and versus different load conditions. So we can see here that we have the fit between the measurement and the simulation on this very important criteria, which is the input impedance. We can check the AM/PM chart. We can check the harmonic power, which is generated as well. This one could be important when we try to minimize the power at the harmonic frequency. Brief check at the output power and the power at efficiency. So here we will not go deep into the detail. It was just to show briefly and quickly how to manage this model into a Microwave Office environment. That's it for the presentation this morning. I don't know if you have some questions. And we can discuss after this presentation, obviously. I will be there for you. Thank you.